from three. Yeah, so we have 3 schools from 3 countries. So we have Zaleka School from Malawi and Yotam Muleya School from Zambia and Motamo Junior School from Botswana. We should be having Mazoya High School from Zimbabwe joining anytime.
Okay. And Knowledge, it's been a pleasure for me to have, now we are 1.5 years into our collaboration. We started collaborating in, I think, July of last year.
Yes.
So it's really wonderful. Grateful to Anika for connecting us. And so we have on our team, we have Kevin McKinnon, so PhD student at the University of California, Santa Cruz. He's in his 5th year of his PhD. The main thrust of his PhD thesis is slightly different from what we're doing today, but it's also related to galaxies and how they form and evolve. The chemical evolution aspect of that is something he's focused on right now. I next want to introduce Dan Espinosa, who's operating the telescope. He's the only one in the whole group who's actually at the telescope, physically at the telescope. And his window says 120 ROR because the telescope diameters are 120 inch or 3 meters, and ROR stands for readout room. So Dan is actually responsible for the well-being of the telescope and making sure that we get striking the balance between protecting the telescope and getting the science observations. We have Rafael Nunez, who got his undergraduate degree from UC Santa Cruz in June. And he is doing research for this year while he applies to graduate school. He was leading a lot of the observations last year. Stephanie Figueiredo is also an undergraduate, but she's a current undergraduate in her final year at UC Santa Cruz. She's currently located in Florida. She's connected from there. Rafael and Kevin are in California, just like Dan and myself. And then we have Stefan Kimura, who's also finished his undergraduate degree and is doing research. He is from, he's in Hawaii. He's based in Hawaii. He's working from there. Monica Soraisam, someone I've been working with for now coming close to 4 years. Monica is in Hawaii. Arya has connected from Hawaii. Arya is a high school student. And the links that are going on the chat, the whole chat is being recorded as well, in addition to video. I thought I would share my screen and show you a little bit about the Andromeda Galaxy. So please bear with me while I bring up a slide set. You should be able to see my slides right now, or will be soon. And in particular, I wanted to show you this slide showing a digital image, actually the same digital mosaic of several images, 57 images, going from left to right, same image, just at higher and higher contrast levels. And these 57 images, about half of them are taken in blue light in the B band, and the other half are taken in the I band, near part of the near infrared part of the spectrum. So it's images taken through 2 filters, multiple images stitched together into a mosaic. This was the first digital mosaic of Andromeda. It was put together by my collaborators and me about 30 years ago, back in early 90s. And what you can see here in the Andromeda Galaxy, you can see the bulge, the disk. It's a frisbee-shaped galaxy. You can see a companion galaxy here. You can see another companion galaxy on the left edge. Now, here's another image, not taken by our group, but by an amateur photographer with a wide format camera. And here you can see the Andromeda Galaxy in a different orientation. the frisbee is more or less horizontal here, and you can see the two companion galaxies very well, NGC 205 and M32. And just to give you some numbers, the Andromeda galaxy is 2.5 million light years away from us. The number of stars is over 100 billion, so 1 with 11 zeros after it. And it would take light about 100,000 years to travel from the left edge of this picture to the right edge of this picture. 100,000 years of light travel time. Light travels very fast. It travels around the Earth 7 times in 1 second. And it travels from the sun to the Earth in only 8 minutes. It takes 4 years to get to the nearest star, but it takes 100,000 years to travel across a normal sized galaxy like Andromeda or the Milky Way. In fact, the overall size of Andromeda and the Milky Way is at least 5 times bigger than this, maybe even 10 times bigger than this. We consider this the inner part of the Andromeda galaxy. And Kevin and Raphael have posted some useful links here on the chat. And you guys, if you...
Oh, these are for a slightly different conversation about the stuff we're talking about, stars and motions and positions and stuff. Yeah, with our...
Gotcha. No problem. No, thanks for clarifying that. And feel free to chime in at any stage. I'm just going to say a couple more things about Andromeda. So the telescope we are using tonight is on a mountaintop in California, but on Monday night, we'll be using a telescope in Hawaii on Mauna Kea, and that picture of that telescope and its companion telescope are what are appearing on the screen right now, the Keck 1 and 2 telescopes, which are segmented mirrors that are 10 meters in diameter. Tonight, we're using a 3-meter telescope in California. Now, here's Andromeda again, and this time you see an outline of a section of Andromeda, and with the full moon to scale and the same 2 companion galaxies. And I show the outline because, you know, we took the first digital mosaic 30 years ago, but a few years ago, we took the largest mosaic, this time not using 57 images, but using 33,000 images with the Hubble telescope. And instead of 2 filters in the blue and infrared, we use 6 filters, 2 in the ultraviolet, 2 in visible light, and 2 in the infrared. And this is a spectacular mosaic, and I'll show you the details of that next. This is a project led out of the University of Washington by Julianne Del Canton, but the Santa Cruz group, students and I have been involved from the beginning. Here is something we're going to zoom into so you can see the details of the Hubble image. We're going to zoom into the Hubble image, so I'm going to remove the label. Here's the arc of the Milky Way going across the sort of top left of the screen, and Andromeda is this frisbee-shaped galaxy 2.5 million light years away. So as we zoom in, the students should get to see a lot of detail, and I apologize if the video is a little choppy. But as we zoom in, you see the details of Andromeda's companions, and soon we'll see even more details of Andromeda's disk and the stars that make up the Andromeda galaxy. We'll see the individual stars. As you can see now, every dot of light with its color is the light of a single star in the Andromeda galaxy. And Andromeda is made up of many, many stars. And we can really see so much detail with the Hubble telescope. That's what I wanted to show through this movie. That's what I have by way of an introduction. I'll stop my slides for now, but we are very grateful to Monica, who has connected us to a project called the Zwicky Transient Factory. This is a project that's based out of Caltech, uses a telescope in Southern California called the Palomar telescope. It's called the Zwicky Transient Factory. And what it does is it takes images, not using a space-based telescope, but a ground-based telescope. It takes images, repeated images night after night, sometimes multiple images a night, and it takes differences between these images to look for stars whose brightnesses have changed or that have appeared where they weren't there before or disappeared where they used to be there before. So when stars change in brightness, they're called variable stars. And when they appear or disappear, they're called transients. And so this project we're doing tonight is we're relying on another telescope to tell us which stars in Andromeda are variable stars or transients. And what we are doing is we're taking their spectra one star at a time to learn much more about the physical properties of each star, their temperature, their mass, their evolutionary state. So we can learn a lot from a spectrum, can measure its radial velocity, how fast it's moving away or towards us. And that's what I wanted to say by way of introduction. And I want to open it up to the team in case Kevin, Raphael, Stephanie, Monica, if you wanted to add anything. And Kevin, feel free to take over the screen share when you're ready. It's very late at night for us, not so much for Monica because it's Hawaii, but the rest of us, it is close to midnight. And in fact, for Stephanie, she's on the East Coast, it's close to 3 a.m. or 2:30 a.m., so quite late.
Yeah, I guess just adding a bit more onto some of the science of what you were saying with these telescopes, not like the one we're using tonight, which is operating as a spectrograph, but the telescopes in Southern California that are taking basically pictures of the night sky over time. They're able to see objects that are changing. And Monica has built a tool that looks at how these objects are changing over time and specifically picks out the ones that are changing in very interesting ways. And very interesting in this case usually means changing in ways that we haven't seen too many examples of. So it's very different than most other objects, most other stars or known types of stars that change over time. And so by studying, by doing the follow-up that we're doing here, we hope to learn about the physics of these stars and learn something new about how stars can form and evolve. So that's kind of the goal here. Specifically, what we're doing is we're taking spectra of stars, which is different than a telescope that just takes a picture of the sky or of a star or patch of sky. What we're doing is we point the telescope at one single star, and then the light from that star enters the telescope and then basically hits something like a prism, and the rainbow of light from that star gets split up onto our detector. And so that's what we're looking at here. This type of spectrograph is one where it splits the light in half. So we have a blue side and a red side, where blue being the smaller wavelengths and red being the larger wavelengths. And so I'll sometimes refer to these two screens here as my blue screen. You can tell it's my blue screen because there's blue coloring here, and then my red screen, which has some red coloring here. And so the light from the star is actually this this central line that you might see in these images here.
Vertical line.
Yeah, this vertical line here, this sharp line. And then that same starlight, if you rotate your head 90 degrees to the left, is this very faint horizontal line here now. So on the blue side, which is what we're looking at now, the bluest wavelengths are down here. And then as you move towards the right-hand side, you move towards longer wavelengths. And then at the edge here is what your eye would see as green. And then we come to this detector. You can stitch them together. So where one stops, the other one picks up. And so at the top here is where this one drops off. So this starts again at green, what your eye would see as green. And then as you move down, you're moving to progressively redder colors, redder wavelengths, to slightly redder than your eye can see. And so
it's green, yellow, orange, red, and then just beyond red, as you said. And then on
exactly.
this side,
And on this side, we go a little bit bluer than your eyes can see.
So it can be ultraviolet, violet, indigo, blue, green.
Exactly. And I'll pull up an example. We're getting close to needing to move to a new star. So I'm going to be needing to be ready for that. Let me just check some stuff here real quick. Dan, I'm going to suggest that we do the last Andromeda target before we do the focus check, just so that we don't lose it before it sets.
Understood.
Okay. Let me just get prepped for that. Okay, so we're almost done on this star. Let's see if I can pull up an example of a bright one where we'll find some features. So this is a much brighter star. You can see the what we call the trace. The trace of the star is much stronger than before. And if I draw a line along here that defines the star's rows, I basically get this image here, which is saying how much light is there in each one of these pixels. And so that's what this image is here. And I'm just going to rescale it.
And it's very broad gamma. You can see
Yeah,
H beta and H gamma.
This is a white dwarf.
Got it.
So this is one of the stars we were looking at earlier. And so basically this is telling you that there's more light at these wavelengths than there is at these wavelengths. And you also notice a few prominent broad dips here. These correspond to elements in the atmosphere of the star. And what we're interested in is basically measuring properties of a lot of these big dips here for the stars that we're interested in, because this tells you lots about the conditions of the star by measuring the shape of this line. Okay, sorry, I gotta pause my speech for a second here. Okay, we are reading out on red. I am sending new coordinates to POCO, and we are ready to move.
And Kevin, if I can just say a quick thing. The kind of star that Kevin showed, white dwarf. Oh, sorry. Let's wait. Let's wait.
Yeah. Dan, I've sent new coordinates to POCO, and we are ready to move.
We are moving.
Okay, and I have a PA of 7.6.
7.6.
Narrowing the slit. And this should be a brighter star at, oh, I haven't pulled it up yet.
And the reason the stars are wiggling around like that is because the telescope is moving.
This is a brighter star at 17.3 megs.
Oh. We have a seriously bright star in the field, so
Yeah.
Yeah.
there, let's try that. So this is our target.
I'm also having a hard time with this. Let me zoom in a bit more.
Try square root.
Square root. Yeah, very bright. Okay, I see a dot.
So you got two field stars, what I believe is our target, and another target just north of it. well, northwest of it. And then this stupid bright thing right here.
Yeah. Yeah, I agree.
So proceeding on the basis that this is our target.
Yep.
Okay, that's a little easier to see in histogram equalization. At least you gave me a nice guide star. And
Is this the last of our Andromeda targets for tonight?
get back in there. There we go. Come on. Thing won't center. You may set your slit.
Slit is set.
And you may begin.
Okay.
And before I forget, can you read off the coordinates of the last target?
The coordinates.
Because I got distracted by something shiny and didn't write down the last target.
That's fair. I may have also done. Give me a sec here. I'll find it.
ZTF 18 ACD ZVPR.
Okay, I did get it written down then. ACD. Okay, RA 003918.7 and deck plus 404742.4.
Excellent. Thank you.
Okay. So we'll be on this one for 15 minutes. Okay. So yeah, going back to where I was before, if we remember this is the spectrum of an example star, not the same one that we're seeing here, but the one I was showing before. And we see these big dips here. Zooming in on one of these things, one of these dips here, these are telling you about the conditions of the star. So if you come in here and you measure the shape of this feature and the strength of it, so basically how much area is in there, it's telling you about, for example, the temperature of the star, the surface gravity of the star. It is also telling you, based on where this line is centered, it's telling you about the velocity of the star in terms of how fast it's moving towards us or away from us. So for example, in a lab, we can go in and we can measure where we expect a particular element to emit or absorb light. And so when we see a feature in a star that we know corresponds to a particular element, we can ask whether that feature occurs at the wavelength that we expect or at a different one. And then by measuring how much that feature has been shifted, the Doppler shift, the red shift or the blue shift, we're able to measure the velocity of that object. So those are some of the things that we're interested in measuring. Each one of these dips corresponds to a particular element. So that's another thing you can measure is by the strength of the feature, you can measure whether an element is present in the atmosphere of a star and by how much. And you'll see these in this particular spectrum. You can see one dip here, another dip there, there's another one here, and you can see that they're getting closer and closer together. And in fact, I know that these are all caused by hydrogen. So as light is emitted from the surface of the star, it passes through the atmosphere of the star. And the atmosphere of almost all stars is, there's a lot of hydrogen in it. And so as the light passes through, if the light is of a particular wavelength, it'll interact with the electrons in the hydrogen atoms that are in the atmosphere. And it might, if it has a particular energy or wavelength, it'll get scattered out of our line of sight, which causes these dips that we see here. And so in this particular case, all of these dips are caused by different orbital or energy transitions of the hydrogen atom. So this is what we call the, or these are all a part of the Balmer series, which means that they're from the second orbital level of the hydrogen atom. This is H beta, so this, basically, as Roger said earlier tonight, to a previous group, what we're seeing is, quantum mechanical effects at vast distances. So we're seeing, quantum mechanical effects in the atmosphere of a star from here on Earth, which is a pretty cool thing.
In fact, these are level 2 to level 4, level 2 to level 5, 2 to 6, 2 to 7. That's what we're seeing.
Right. Yeah. 2 to 4, 2 to 5,
6,
2 to
and
6.
you can barely see the 7.
Yeah, down here. And then if I found the corresponding image on this side, we could find the corresponding transitions. So that's the information from the star that we're interested in. There's a lot of other things that you might notice on the screen here. So other than just the faint line from the star, we're getting a new readout. Other than just the trace from the star, this white line from the star, you see these vertical barcode looking patterns that span almost the entire vertical range here. And these are caused by the Earth's atmosphere. And in this case, again, it's been rotated. So you're looking at horizontal bars here. These are caused by the Earth's atmosphere because, as we open the telescope up, we're looking at these stars, but light is entering the telescope from the Earth's atmosphere as well. And, as a surprise to me when I first started astronomy, the Earth's atmosphere is actually pretty bright, even in the middle of the night. And so that's what we're looking at here as emission from the Earth's atmosphere. And so later on, when we're trying to use this data for science, we need to remember to remove any chemical signatures from the Earth's atmosphere. So those are some of the main screens that we're seeing here. Basically, these screens allow me to configure some of the telescope settings, to choose exposure times, to interact with the data as it comes in, as I've been showing you. And we have a few other screens. So for example, this one, maybe you saw earlier, I have a list of the targets that we're interested in with a few key features, things like their position on the sky and their brightness. I have also this image right here, which is kind of like a webcam of the sky, which Dan uses when we get over to our target to maneuver the telescope so that only the light of our star that we're interested in is entering the telescope. And so if I zoom out a little bit here, you see kind of this funky shape. And really what we're looking at is a polished piece of metal that has a gap in it. That's why you see this stripe here. So the polished piece of metal is reflecting the sky. And so there's a webcam pointed at this polished piece of metal, and we see some bright spots from the stars in the nearby area. Whoops, I have to zoom in. And then Dan is able to move the telescope very finely so that the light of the star that we're interested in falls right in the middle of the slit. So it's kind of hard to see, but there's a few stars here. There's a really bright one that Dan has locked the telescope onto, and we use this for guiding. So the telescope knows that we want to make sure that the telescope is following this star. So if the star looks like it's moved, the telescope will move itself to bring it back to where it should be, so that we're tracking objects across the sky. And then our target is right in the center over here. And then finally, the last screen that we also look at has to do with the weather conditions on the mountain. Some weather information over here about rain and dew, wind, stuff like that. And then also some nice webcams to see the current condition of the sky. So right now we're pretty lucky. We had some clouds earlier that were being a little bit annoying, and they seem to have cleared up mostly. I can see a few off in the distance, but for right now we have some good conditions, and you can see the Milky Way beautifully across the sky here. And so that's most of the information. On my other screen over here, I have some logs that we're keeping of how the night's going, and a list of our possible targets and stuff like that. So that's most of what you're looking at here, and I'll leave it to the rest of the team to remind me of anything that I may have forgotten to say.
Well, this is great, Kevin. Thank you. The white dwarf you were showing, I just wanted to remind people that a white dwarf is a type of star that's dying, and that's what our sun is going to become in about 5 billion years. It's going to die as a white dwarf. And ironically, when stars die, they become very hot because they lose their outer layers, and you can see into their inner, much hotter portions of the star. So that'll happen to the sun in about 5 billion years, become a white dwarf, and it'll cool. After that, it'll cool for a good 10 billion years as it loses energy. But when the sun becomes a white dwarf, it's no longer running the nuclear fusion reactions that power it and keep it steady. When it loses its nuclear fusion source, what happens? It can only cool down over time, cool down and get fainter over time, which is what white dwarfs do. This is a great time to ask questions for the students. If there's anything that you've seen that looks interesting or looks confusing, you don't understand something, feel free to ask. We'll do our best to answer.
First, I just wanted to check, Stephanie, are you on the call still or around?
Yeah.
I was wondering, for these transients, could you put in the like time to peak air mass or something? I'm trying to decide the order that I should observe these.
Yeah. One of them is a must do, like ED2 must do. So should we do that one instead of ED3? Or will we still be able to do ED3?
Sorry, I'm not sure which one you mean.
Like on your chart, it says like ED2. And then that's a must do one. So will we not do ED3, like the one on top, or?
Oh, no, these, sorry, these aren't the same. These aren't the transients.
Oh, okay. No, it just looks like it.
Yeah.
But there's like an instance of that. So do I just erase one of them? Or yeah, like.
Yeah, I'm just looking at your transient plot here.
Yeah, so 6 and 5.
Mm-hmm.
So number 6 is a must do priority.
Okay.
So it's like right under 5. So
yeah.
Are we not going to be able to do 5?
We'll probably be able to get 5 as well. This solid line being the middle of the night, which is kind of where we are right now. Yeah, we'll probably be able to get both of them. I don't think we'll be able to get 4 and 5 and 6. But
okay.
yeah, I'll go to 6 right after we do a focus check.
Okay.
So for those of you watching at home, we've been mostly looking at stars in Andromeda for the first half of the night. But now that Andromeda is starting to set, we have targets to fill up the second half of the night. And these are transient stars. So these are the kind of the interesting ones that I was talking about earlier that have been identified as particularly weird and not well understood. Well, yeah, anyway, so we're going to be going after those to see if we can classify them before any other groups can. And if they're particularly interesting, we send out alerts to the rest of the community who might be interested, saying, hey, if you're interested in this object and this thing is pretty cool, you should go check it out with your telescopes.
Real quick, Kevin, what area of the sky are we going to for transients?
We're going to RA 3.5, deck -2.
Okay, so air mass will be kind of similar then. Thank you.
Knowledge, after we end today's Zoom call, I'll send you a recording as before of the chat and as well as the video. You're welcome to share that with the schools. And Arya, you've been such a regular visitor from Hawaii. Thank you for connecting. Arya, are you on Oahu or the Big Island? Oahu. Do you know Iolani School?
We are reading out on red, so you're free to take the telescope for mirror alignment and stuff.
Okay. It'll be just a couple seconds.
Okay. Oh, I guess we got that bright one right there. Convenient.
Seeing is not great. Get the feeling it's degraded some since we opened.
Yeah, it started at 1, so we were doing pretty good at the beginning.
Let's try that. Get the feeling I'm not in the greatest place to focus. Let's try over here. So that's 13.5. All right. New seeing estimate is approximately 1.8 arc seconds.
Oh my gosh. Okay.
It might improve slightly when we change air mass here. Go ahead, send your new target.
Sending new coordinates POCO, and we are ready to move.
605. And we're off.
And I have a PA of 197.
Oh, yeah, I know why the seeing is a little off. I forgot to adjust one thing. So yeah, it's probably better than that.
Okay.
Say again your PA.
PA is 197.
197. Yeah, this is pretty dim. What's the expected brightness when I actually get on this?
It is 18.5.
Look, and you start slew. Okay. My reading is this is their target.
Oh, wow. I have to rotate my head a lot. Yep, I agree.
Okay. And we want that one. You may set your sled. Oh, that is not going to be a good pet object. And you may begin.
Okay, and we will be here for 40 minutes.
40 minutes.
40 minutes. So for our visitors, now would be a good time to ask questions if you have any.
And I'll do my best to help answer also.
I'll probably defer to you.
And all questions are welcome. It doesn't matter if the question is not exactly or directly related to something you saw on the screen today. It could be something related to some other aspect of astrophysics or careers or telescopes, anything at all. We're open to any kind of question.
I'll step out for a second.
Yeah, just excuse me, from Zaleka Secondary School in Malawi. There's a student who has a question. Can you
Please go ahead.
Yeah, we want to see the telescope and how it works, like the picture and how it works.
Could you please repeat the question?
I'm saying we want to see the telescope, the image of the telescope and how it works.
Ah, I see. Let me see if I can, we don't have a camera. I don't think we have a webcam inside the Shane 3-meter dome. So-
Not currently, but you can look at HamCam 2, which shows the dome that it's in.
Oh, okay. HamCam 2, let me look it up.
In the meantime, I'll see if I can find an image of it online to direct you to.
Okay. I'm on HamCam 2, and it is showing images of the observatory rather than of the telescope itself.
Yeah, so on HamCam 2, there's
Uh-huh.
a large dome just right and just below center frame. And that's the dome the telescope we're using is in.
I see.
And then if you go to the mtham.ucolic.org or mounthamilton.ucolic.org
Mhm.
website and click telescopes, and then user guide for the 3-meter Shane reflector.
Telescopes, user guide for the, got
Yeah.
it?
And you'll need
Oh,
to
beautiful.
share your screen
Yeah, beautiful.
because right now we're still seeing the red spectrograph readout, not the HamCam 2 or what you're showing,
Got it.
what you're looking at, sorry.
So Kevin, can I please share my screen briefly? I'm going to take over Kevin's screen.
And then, Raja, if you click on that image that comes up with the Shane, you
Uh-huh.
get a, yeah, it's not fully, there you go. And then you can zoom in a little bit on that.
That's what I'm trying to do, okay?
So, looks pretty good on your screen from where
Good, good, good. This is what the telescope looks like. And each, you see the railing over here, that's about half the height of a person, just to give you a sense of scale.
Yeah, it's just over 1 meter high.
Does that answer your question about what the telescope looks like?
Yes, we have seen it.
I think the other part of the question was about how it operates.
Uh-huh.
Do you want to cover that, Roger, or you want me to?
Please do, Dan.
Okay, so you see in the center of the frame, there's a big ring connected to a tan colored structure. And that's the pivot of the telescope, so it can swing back and forth along that axis. And then the tan portion, there's another identical piece on the other side of the telescope you can't see in this picture. That can twist clockwise and counterclockwise. And the combination of those two movements allow you to point the telescope anywhere above the horizon. Then at the top of the telescope, there's what's called the secondary mirror. But light comes into the telescope around the secondary mirror, goes all the way down to the bottom yellow ring that you can see, where the primary mirror, which is 3 meters in diameter, it's very slightly dished. It's, I think, 8 inches, 20 centimeters deeper in the middle than at the edges. At any rate, Raja has just taken away my visual aid there.
Oops, I'm sorry. I'll bring it back. There you go.
Yeah, so light comes down through the telescope tube, bounces off the primary mirror up to the secondary, and because the mirror is curved, the light that's reflecting from the primary to the secondary looks like a cone. And then from the secondary, it reflects back down through the primary mirror. There's a little hole that's about 10 centimeters in diameter into the instrument, which hangs below the primary mirror. And the instrument contains a couple of prisms and a couple of what's called diffraction gratings, which scatter light into the rainbow that I think we were talking about earlier. It's a very similar effect if you hold up a CD or a DVD disc to the sun and you see the rainbow colors. And then there are two cameras that record the rainbow, and that yields the readouts that you were looking at on Kevin's screen. And by knowing what the intensity at each position in the rainbow is, we know what the intensity of the light coming from the star was. And then by knowing some physics, we can figure out what elements are present in the star. Raja, you can talk more about that than I can because you understand the instrument better than I do.
Yeah, the instrument is a double spectrograph. So once the telescope, as Dan said, light bounces off the primary mirror, then it bounces off a secondary mirror. It goes through a hole in the primary, and that's where the spectrograph sits. And one of the first things that happens is light goes through something called a dichroic, which is a piece of glass that reflects light shorter than one wavelength and transmits light longer than that same wavelength. So it splits up the light into two separate beams. The blue shorter wavelength light, shorter than about, in this case, we're using the D57 dichroic. So light whose wavelength is less than 0.57 microns goes into the reflected part of the beam, and light whose wavelength is longer than 0.57 micron goes into the transmitted part of the beam. And each one goes into a spectrograph that has gratings or prisms and splits up the light into the rainbow that Kevin was showing.
So Raja, if you want to show that schematically, if you go back to the 3 meter and you choose, oops, let me
Should I
make
go
sure
back
I
one
give
more?
you. So you've got the introduction,
Uh-huh.
and you click, what is it? Instruments cast.
Instruments.
So that's the first link in the white part of the page, cast spectrograph.
First link and the, am I on the
So-
correct page?
Yes.
Next to Casagrian.
Oh yeah, I see it.
there.
Thank you.
So if you click that, it'll give you and then you hit on all the way over on the left, hardware overview, it'll give you a schematic of the instrument.
Got it. Ah, there we go. Beautiful. So the dichroic would be, let's see,
And letter C.
this thing here. So yeah, okay. So you can see what's happening here. Light is coming from the telescope, focused light through the mask, and then when it hits this, some of the light goes straight through and off these things into this camera. Some of it bounces this way, bounces off element D and goes into this camera. And it's got prisms over here. This one's got gratings and prisms. Both of them have the function of splitting light into the colors of the rainbow. So you can think of light coming down from the telescope. This entire thing is hanging below that image you saw before, or image of the telescope. It's hanging below that at what is called the Cassegrain focus of the telescope. Thank you. This is great, Dan. Thank you for taking us through these schematics of how the telescope and instrument work. So generally, the telescope focuses light, and then the instrument takes that focus light and does something with it, either creates images or spectra. Are there other questions? That was a great question. from any of the other schools as well.
So another place on the page that you can go,
Mhm.
again, from the LIC website. Now I've
I'm going to
lost
go back to that page. Okay.
information of general interest on the right-hand side, and then telescopes and instruments all the way on the left-hand side. And then if you click the 3-meter Shane reflector, it shows another picture, a clearer picture of the telescope itself, a picture of the dome with the laser operating. And then if you scroll down a little bit, it shows the mirror, and scroll down a little bit further, it shows the different ways the light goes through the telescope.
Am I starting on the right page here?
No. Go back. Okay, down one from there. Information of general interest on the right, on the right, on the right, further right, down.
There we
There.
go. Thank you.
And then telescopes and instruments, all the way on the
Telescope.
left.
Thank you.
There you go. And then first link.
Okay. Oh,
There's
beautiful.
a picture of the Shane and a picture of the dome.
Beautiful.
And the line coming out of the dome is the laser that we use for adaptive optics, which gives this telescope the ability to make images as clear as the Hubble telescope.
It untwinkles the light of the star, of each star, by countering the effects of the atmosphere, by countering the effects of turbulence of the atmosphere.
And then Raja, if you'll scroll down a little bit,
Mhm.
a little bit more, that is the main mirror for this telescope. And you can
This
see
one.
the size of the people next to it to give you a sense of scale.
Yeah, I guess 3 meters is about 1.5 times the height of the 3-meter diameter is 1.5 times the height of a tall person.
I'd say 1.5 times the height of the average person.
Okay.
And then if you scroll down just a little bit more, that image is kind of hard to see on Zoom, but it gives you the 3 different paths light can take through the telescope.
So prime
right.
focus, where bounces off just the primary mirror and comes to a focus here. Cassegrain focus, where it bounces off the primary mirror and then the secondary mirror goes through a hole in the primary. And the Coude focus, where primary mirror, secondary mirror, and then a tertiary mirror and goes off to the side. Coude
And
means elbow in French.
And we're currently using Cassegrain focus.
So using this middle one. So our instrument is hanging off the bottom of the telescope.
Wow, there's some really old images of the control down below
Yeah,
that.
I see that.
So, at any rate, I hope that starts to answer the question. I forget who it was that asked, but I hope that begins to answer their question.
This is great. Thank you.
Stephanie, I've changed my mind, and I think we will be able to get all 6 of the transients. We might even need some more.
When can we do the first one?
We're on the first one right now.
Oh, okay. So wait, can you go back to the So when can we do the CO, like the first red one?
Sorry.
Because I didn't include that one. The first red bump.
Yeah,
like
we
when
should
will
be able to
we
get
be
that
able to do that?
next. Yeah. We'll finish this
Oh, okay.
comfortably, and then we'll have enough time before it sets, and then we'll go on to this one, then this one, and then these two. Yeah, it'll all fit, I think. I say now. We'll see.
Okay.
Yeah, especially since this first bump one is brighter than the others. So
Yeah, that makes sense. Actually, I can put like the time.
There's a question on the chat. How exactly does a radio telescope function to show the stars from the Earth? So radio telescopes work in the same principle. Light bounces off an antenna, comes to a focus, except it's using radio waves, not light. And generally, stars are not the main target of radio telescopes. Radio telescopes often look at other things, like the ALMA telescope looks at things that it could look at planets. It also looks at very young stars, not normal stars, but very, very young stars that are still bright at radio wavelengths. It looks at quasars and AGNs. But radio telescopes work at the same principle. Light bounces off a mirror, comes to a focus, etc. Now, the difference is radio waves can't be seen by the human eye, but they can be captured by radio dishes. This is actually true of many kinds of astrophysics: gamma ray astrophysics, ultraviolet, gamma ray, X-ray, ultraviolet, infrared, microwave, submillimeter, radio waves. These are all kinds of radiation that the human eye cannot see, but there are special purpose telescopes that can.
one of the fun things about radio telescopes that maybe you don't think about, or I didn't at least until I saw my first one, is that they can operate 24 hours a day. Because when we're looking at the light of these stars here, we have to wait until the sun sets because it's so dominant, right? Absolutely blots out the stars during the day. But the sun and the Earth's atmosphere, aren't significant sources of radio waves. And so, it's basically nighttime all the time if you're looking through a radio telescope. And so a lot of radio telescopes can operate all the time. And in fact, can operate with a piece of fabric or something covering the telescope to keep it safe from the elements, because that doesn't block any of the radio signals. So it's pretty funny to see, what looks like a telescope that's covered up, but it's operating all the time.
That's a great question. Tumelo has asked, which is the largest star in the Milky Way? As far as I know, there's a star called the Pistol star, Pistol, that whose mass is about 100 times the mass of the sun. 100 times more massive than the sun. And as far as we know, stars don't get much more massive than that. They don't, for example, get to 1,000 times the mass of the star of the sun, or 300, 200. 100 is about the limit. And there's a concept called Jeans mass that has to do with how material fragments, but you don't get fragments that are bigger than about that.
And also, from the other direction, stars are, pushing out a certain amount of energy. So there's something called the Eddington limit as well, which is kind of the rate at which a star that would be so massive would explode itself apart based on the energy that it was making. So both of those things together kind of set the theoretical upper limit of how big a star can be.
And in the lower limit, a star has to be at least 8% of the mass of the sun. So 0.8 times the mass of the sun. If it's any less massive than that, it's not hot enough to start fusion reactions. That's called the hydrogen burning limit, where burning refers not to chemicals, not chemical burning, but nuclear fusion. That's a great question, Tomato. Thank you for asking. I'll be right back. I just have to plug in a device. I'll be right back. What kind of star is the Pisto star? You should look it up. I'm not certain. It's what would be called an O star in terms of its spectral type, very hot and very massive.
So one of the things that we'll also do when we're heading to really faint stars, like we will be after the one we're looking at, is give Dan a finder chart. And that's what this is here. So basically there's a historical image of that portion of the sky, which is what we're looking at. And the thing that we are interested in is going to be something that's very faint at the very center of this image. And so in this image, it doesn't even show up. And so these dark spots here are nearby stars and sometimes galaxies. And so what I do is produce a chart. Oh, that failed. That's not good. I'll get a working example in a second. I will measure the distance to these nearby bright stars, and so we can use those to offset so that we can make sure that we're pointed at the correct patch of sky.
The question your term is asking is why are black holes not visible? They have such intense gravity that not even light can escape from them. You know, Einstein's theory showed us that light can be bent by gravity, and a black hole's gravity is so intense that light is bent back onto itself, doesn't escape.
So your finder chart arrived, Kevin. Is this thing really that dim?
It should be pretty bright right now. It's just that's the image. That's why I sent it just in case. It is fading, but it says it's like 18.7 megs. Or sorry, 17.7 megs.
Okay, that makes a big difference.
Yep.
We'll try it. Otherwise, you might have coordinates for blue ready.
Okay.
We got what, about 7 minutes to go here?
Yep.
Got it.
See, there's a question in chat about what is a galaxy and how many have been explored. A galaxy is surprisingly kind of difficult to define sometimes, depending on who you're talking to. But in general, it's a collection of stars that are gravitationally bound to each other, and that mostly just means over time they're not going to fly apart from each other. Given if they were left alone by themselves, they'd continue to orbit each other and stay together. So that's kind of what a galaxy is. So our galaxy, the Milky Way, is one example of that. If you left it by itself, it continued to spin in this nice disk that we see. Andromeda is another one. But over time, galaxies tend to grow by smashing into other galaxies to combine and make bigger galaxies. And so over time, Andromeda is going, our nearest neighbor, big galaxy, is going to crash into the Milky Way and make a larger galaxy at the end of that. How many have been explored? If you mean like how many have we been to, or humans have been to, just the one, just our galaxy. This is, we've never even made it outside of the solar system. We've only been able to explore our solar system, which is very, very, very small compared to the size of the galaxy. If you mean how many have we, studied, I don't know the answer to that question. Raja, do you know how many galaxies maybe we can see?
I could give you a rough sense of that. There is, roughly speaking, 50 galaxies per square arc minute on the deepest Hubble images.
Wow.
And, so there's 40,000 square degrees in the sky. Each square degree is about 4,000 square arc minutes. So it's 40,000 multiplied by 4,000 multiplied by 50. So let me think about what that is. 40,000 multiplied by 50 is 2 million. Right, 40,000 multiplied by 50, I think, is 2 million. Multiply that by about 4,000. So we're talking about roughly 7 to 8 billion galaxies in the visible universe.
And each one of those has, well, a different number of stars, but
100 billion
our galaxy has 100 billion stars.
That's not an unusual number, because our galaxy is a pretty typical galaxy. And the one thing I would say also about galaxy definition is when you have small enough collections of stars, we tend to call them star clusters, not galaxies, unless there's evidence that they contain dark matter. So the smallest galaxies contain about as many stars as the bigger star clusters in our inside the Milky Way. But the difference is the smallest galaxies contain dark matter and the star clusters don't. And one of my former students, Marla Jeha, works at sort of that intersection.
I was just going to add on that little point of I thought galaxies also had something binding them aside from the stars and gas and dust.
Gas and dust, yeah, good point.
There's a great question in chat from Arya about, since the universe is expanding, does that mean eventually our galaxy will be all alone, or will our local group of galaxies stick together? You've basically hit the nail on the head, which is to say that in general, on the largest scales, it seems like our universe is expanding and expanding at an accelerating rate. So things that are farther away are getting farther away fast. Even to a degree that if we were, to travel at the speed of light, we'd never be able to reach them ever. And but locally, on smaller scales, on more nearby scales, gravity is a stronger force than the expansion of the universe. And so things within our local group of galaxies are ultimately destined to come together. But, in the far, far future, basically what this means is you'll have pockets of space where there are, stars and planets and all this stuff, and then vast stretches of empty space with absolutely nothing. And so, it's really interesting that we, are alive at this time where we're able to see distant galaxies, where we're able to see lots of nearby stars, where we're able to see, a beautiful night sky, because in the very, very distant future, way longer timescales than even the sun dying, the night sky will be pretty boring in comparison to what we're able to see today. So, you know, for that, I feel lucky.
It's great questions.
Mhm. Okay, we're reading out on red. I am sending new coordinates to POCO, and we are ready to move
Here we go.
to our interesting target.
We have a PA for this.
In just a second. I have a PA of 108.
108.
So we don't know of spaceships that can travel faster than light. And we think the universe has a finite beginning in the Big Bang, but we don't necessarily know that it has a finite end in the finite future, that is. So the universe is often thought to be semi-infinite, that it has a finite start time, but it has no end time. And the start time is often known as the Big Bang.
I think for a while, even 20 years ago, there was kind of a debate about whether the big crunch idea, this idea that maybe the universe collapses back in on itself and then starts over or something like that. But I think our current understanding rules that out, and the idea is that the universe will keep expanding. So there's no end.
Okay.
Oh, this is a dense star field wherever we are now.
Mm-hmm.
And of course, the other historical image is broken. There we go. Okay, so okay, I know where we're at.
Yeah, I can see our target.
Okay. Yeah, that's it right there.
Yeah. Phew.
That's gonna make life easier. Let's see.
These are great schools, by the way, that you guys are attending, because you're learning so much and you're asking such amazing questions. So Motamo Junior School, what is the range of grades in your school? Is it like, or maybe I should ask, how old are the students, the youngest students in the school and older students in the school?
You may set your slit. And you may begin.
The one who is youngest.
Kevin, is this the first of the non-M31 transients?
No, this is the second.
So I heard some noise that sounded like a school opened their mic, but I did not hear an answer to the question.
I didn't hear a question, actually.
It was your question, Raja. What was the range of?
Oh,
student
yeah, okay. So either. Did the Saleka school want to ask a question?
Yeah, we just want to say like on age. This one is the youngest. Actually, is not in there. The youngest is 18 years. Huh? The youngest is no, the oldest. The youngest is 14 years.
Is it 14 to 18?
Yeah.
Okay, that's like high school.
What he's saying is that here at Zaleka Secondary School, the youngest students are around 14, 15, and
Okay.
the oldest students are 18 and 19.
Okay, that's very good. Thank you. That's like high school. And you call them forms, right, in Africa?
Yes.
Forms. So is it form 1, 2, 3, 4 or something like that?
Exactly. It's from 1 to from 4.
Okay. Forms 1, 2, 3, 4 are part of high school. Okay. Are you having fun?
Yeah, it's fun. So it's a bit advanced for us. Some stuff are a bit advanced, so it was fun to learn new stuff.
You're learning some new things. Oh, I realize my video is off. This is what I look like.
Yes, sir. We have a question here. Sir?
Yes, please. Please ask the question.
Yeah, I would like to know other application of a telescope apart from zooming the stars.
You know, the main purpose of the telescope, more than zooming, because it is so much bigger than a human eyeball, you know, 3 meters in diameter or 10 meters in diameter, it can collect more light in, let's say, 10 seconds or 5 seconds than the human eye can in the same unit of time. So it's much more sensitive than the human eye in collecting information. It's much more efficient and sensitive than the human eye in collecting information about the stars. That's really the power of a telescope. Yes, sometimes it's used to zoom in and see detail, but most of the time it's used to collect more light than the human eye can, and therefore get some information out of that light. Like Kevin was saying earlier, we take a spectrum to learn about the physics and chemistry of the star, how fast it's moving, what its temperature is, what its mass is. That's really how telescopes are often used, is to learn about the workings of stars, galaxies, dark matter, dark energy, the universe. Does that answer your question?
Is it the gravitational force of the black hole that keeps stars together?
That's a great question. The stars in a galaxy are not held together by the gravitational force of a black hole, but instead they're held together by the combined gravity of all the dark matter and the stars that make up a galaxy. There is a black hole at the center of the Milky Way. There's a black hole at the centers of most galaxies, but their mass is very small compared to the mass of the overall galaxy. Less than 1%, about 0.1% of the mass of the Milky Way is in the central black hole. 99.9% is in dark matter and normal stars.
From this question, like, if it's not the black hole which keeps the stars together, like with this gravitational force, but it's the collective masses of these stars that keeps them together, then what is it that separates galaxies like the Milky Way from all other galaxies?
That's a very good question. So it's what defines the boundary of a galaxy is, so suppose you have the Milky Way and the Andromeda Galaxy. If you have a star that feels a stronger pull from the Milky Way, it tends to orbit the Milky Way, and we call that a member of the Milky Way. If there's a star that's closer to the center of Andromeda and it's orbiting Andromeda, we call that star a member of Andromeda. So that's what defines the boundary of a galaxy, or what star belongs to what galaxy. It really is determined by what it is, which galaxy's center it is orbiting. Does that help answer the question?
Yes, it does. Thank you.
In fact, this question of where our galaxy ends is of great interest to me. This is something I'm quite actively interested in right now, trying to define the outer boundary of the Milky Way, for example. Sorry, Ephraim, could you repeat your question? Ephraim, were you trying to ask a question? Were there other questions from the group? Any of the groups? Yeah, Arya, to answer your question, as Raphael says, you can think of a neutron star that feels it's a star that can't survive as a white dwarf. The sun is going to end as a white dwarf, but if you pressure a star enough because of its own mass, what happens is atoms collapse. Electrons get crushed onto the nucleus. Electrons and protons combine to form neutrons, and it becomes a neutron star. And the limit at which this happens is 1.44 times the mass of the sun, the Chandrasekhar limit. I don't think we understand why there is no liquid water in Mars, or in fact, if there is evidence of liquid water or not on Mars. I haven't followed the latest on this, but often you don't see liquid water on a planet because it's too cold or too hot. If it's too hot, it's in the form of steam. It's too cold, it's in the form of ice. Mars is just on that boundary. It's a little too cold.
I think current thought is that there is liquid water on the surface of Mars today.
Okay.
And the other aspect of that is the atmospheric pressure. And Mars is small and doesn't have a very big magnetic field, so it doesn't have much atmosphere. So liquid water tends to become vapor water pretty fast.
Mm-hmm. The answer to your question is no, generally. A star can't turn into a planet. What distinguishes whether an object becomes a star on a planet is its initial mass. Again, it has to be more than 8% of the mass of the sun, 0.08 times the mass of the sun to turn into a star. And anything less than that, it either becomes a brown dwarf or a planet.
I think there's also a a difference in terms of like the formation mechanism, in terms of like, did it grow from a collapsing glass, or was it created from a collapsing gas cloud, or did it form from a bunch of small pieces of dust that started sticking together and then built up to become a planet?
Yeah, that's a great point, because like the star is kind of like the center of a spiral that happens. And then the planets are kind of just what collapses outside of that center of the spiral. That makes sense. I don't know if you guys have seen stuff about like how a star forms and like the protoplanetary disk around it and all that, but the star forms in like the center of a very, like a spiral that starts off kind of slow and it just picks up speed and more and it collects and blah, blah, blah. But yeah, long answer.
I'm getting very tired. I might take a short nap.
That's fair. Take some breaks.
I'm going to stop recording.